All right, it's 1 o'clock, so why don't we go ahead and get started? Everybody, welcome back to Python for Physics. As always, we got to start with a little bit of administrative bits. So first, if you're new to the class, welcome. If you've been following along from the beginning, welcome back. If you're new to the class and this is the first class that you're listening to, you can join the live stream. We're starting to build on content that we've previously taught. And so some of the stuff might not make much sense to you, in which case you can look back at the old videos and try to catch up. I see that many of you have been looking at the previous videos. They're there for you, so please take advantage of them. Feel free to share them with your friends and anybody. They're free, and yeah. And so just for some context, this is a class that Professor Ted Rogers and I are co-teaching, and we have several TAs that are assisting with the class that are in this call. And so let me jump into administrative stuff. So if you're new to the class or you're still a little bit lost about all the different links that you're needed to bring you up to date, what you have to do is just send an email to pythonforphysics@odu.edu. Every single time I mention this, many of you send emails, and so you can just send an email, and what you will do is you will get an email back like this. So you'll get an auto reply stating all the different links that are needed for you to be able to get up to date. And so here is the link to our main page. There we try to answer many of the questions that you guys have been asking. We open up a Slack chat where you can interact directly with us and ask questions. And I've been talking to several of you on one-on-one chats, just trying to help you build your codes and debug your codes and polish your understanding of what is being taught. There is a little bit of a caveat that is worth noting, that Slack has a policy that only 16-year-olds and up can join the Slack. So use your judgment wisely there. If you're seeing this in the live stream link, this is the one that you should be using. If you're seeing this in the recorded session, you want to join the live stream, so you can just follow this link. And then all the recordings are posted either in the ODU Regis page or separately in these two pages. We also have a Dropbox links where we're sharing all of our slides, all of our code, and they're available on this Dropbox link, so you can go there. Also, we've generated so let me first show the page. So here's a page where we've been putting many of the answers to the questions that you guys have been asking. We've also given you some different resources. People have asked for, let me close the Slack, because I see that some of you are already joining as I speak, and so I'll keep getting reminders. And so many of you have asked for us to translate the material to Spanish. We are working on this, and so be patient. We'll do this in the next few weeks. And also, we've been putting some of your nice quotes at the end of this page, and so if you have been sending nice quotes, I've been asking for your permission and putting them there, so you can go check them out. If you want to say something that to be put on the page, go ahead and send us an email or a comment, or something positive, what this class means to you, how you think this class is useful for your career. Something interesting would be great. It would be good to hear what you think you're getting out of this that would be relevant for your academic career. So if you send us that, then I'll gladly put it on our page. And the last thing is that we created a Dropbox folder for you to show your code, and there you can show your code to us so we can look at it. In fact, I was talking to somebody yesterday who put there from, I think it was from Canada. So I was talking to somebody from Canada and India about their code, and one of them, I think the person from Canada, put their code in Dropbox, and then I was able to edit it on the fly and fix the bug and then send it back to them automatically. So if you want to have that kind of interaction, then send us an email with Dropbox access as the subject line, and then we'll be able to get you access to a Dropbox folder, you can make a little folder with your name, and then you can start putting your code there, and we can look at it more closely. Also, we can see what you're doing under the hood. Okay. So that's all the administrative stuff that I have for today. So this is the second part of a two-part lecture that started on Tuesday. And this is supposed to be the beginnings of giving you an introduction to data analysis. And so we covered a little bit of basics of probability, statistics, in the first half. On the second half, we're going to starting to introduce some basic aspects of particle physics, relativity, incorporating those things to our data analysis. And so that's what we're going to be touching on today. So I figured I would start with a little bit of recap and then also address some confusion points, some of which I introduced and some that I didn't really completely clarify in the last class. So let's start with just recapping some of the key points on the data analysis part, and in particular regarding statistics. And so the first point one of the first things that we started introducing was when you do some sampling of some population and you acquire data describing that population, you start collecting your data. When you collect your data into an array, we're going to be referring to these as distributions. And so let me consider a distribution of n data points, which in this case was regarding heights of people, but you can just think about it could be anything about, it could be weights, it could be any feature of individuals. It doesn't have to be about individuals, it could be of particles or anything, okay? So xi is just a generic quantity that we're measuring some population, that it could be people, it could not be people, it could be anything, right? And so this is going to be n component, there's going to be n measurements associated with this data set, and they're going to go, so I'm going to label that the elements in this set from x1 all the way to xn, okay? And so if I want to calculate the average of the distribution, all I have to do is just sum over each one of the elements of that distribution and divide by the total number of elements in that distribution, okay? And so I just sum over all xi's and I divide by n, and that gives me the average. And I'll try to be consistent with my notation and refer to the x bar with a little bar on top, this little symbol on top. That's going to refer to the average, okay? And so here are some examples of what this looks like. So you can just grab, if you have a data set of 2 points, 55 and 60, the average is just the sum over the 2 divided by 2, because you only have 2 elements in that set. And then same thing with this other one. So in this case, you have 3, so you have to sum over each one of those 3 and divide by 3. And so you can test out, you can write this in Python, you can test it out with a pen and paper and just make sure that you agree with this result. Okay. Okay, so the place where I was a little sloppy and I wasn't absolutely clear was on the definition of standard deviation. So there's different definitions of standard deviations, and they depend on what we mean. Okay, and so first, the definition that I introduced was the standard deviation of a sample of the whole population. Okay, so imagine you have a population of that has n prime elements in that population, and I only sample n of those. So I sample less than n prime, and so in this case n is less than n prime. Okay, and so a quantity that tells us about the spread of this distribution is a standard deviation. And in this case, this definition with the n minus 1 is referring to this scenario where I'm sampling only a subset of the total population, okay? And this we're going to refer to as the standard deviation of the sample, or the sample standard deviation. And this is a definition that we'll be largely using unless stated otherwise, okay? And as I mentioned, we're going to be thinking about distributions that are largely Gaussians, and we introduce what that means, or they're Gaussian or normal distributed, and I introduce what they mean. And the standard deviation, what it's telling you is roughly where 68% of the sample set lies, okay? And this is true when you have the complete population, and this is approximately true when you have a subset when you have a sample of the total population. And here to clarify this, I put a slide that is a little bit loaded, and it ultimately doesn't really matter that much, but it's to clarify these questions about why we were dividing by n-1 versus n, and it comes back to the fact that I mentioned that there's many different ways of defining standard deviation. Each one of them gives you different, they're more sensible when you have different, for different scenarios. And so here, the example that perhaps some of you are more familiar with is when you sample the full population of the system. So imagine that I wanted to do some, for example, measure the political leaning of all of the people in the United States. If I were to sample all of the people, everybody in the United States, which would be roughly 300 million people, and I wanted to understand the average leaning political leaning of the people, I would take the average of that, and I wanted to have some quantitative measure of the distribution. Perhaps political distribution, political leaning does not make much sense. So let's think about heights. So the average height, and I wanted to estimate the spread of the height, and I've sampled everybody in that population, then I would use this definition of the standard deviation. If instead I don't have a means to ask the height of everybody in the United States, but I can sample a subset of people. So imagine that I only sample people in Virginia, so that's a subset of the whole United States. Then the standard deviation definition that I use is that of the sample that associated with the sample of a population, where I've sampled a subset. And this is a definition that we introduced last time. And this is here, what we're doing is not really calculating the full standard deviation, but we're estimating the standard deviation of the set of the population, because we don't have a means to access it completely. And so that's where this n-1 would appear. If the limit the n is large enough, these two don't make much of a difference. Which is why I said that it doesn't really quite matter. And here this is not a course in statistics, so we don't have to drive where these, why are these definitions, when they're more useful than others, but they're just, we're supposed to be mainly thinking of ourselves as practitioners of statistics. So we're going to be using these definitions and try to apply them in different scenarios. And then instead, for example, if you wanted to estimate the error of the mean that you've obtained with a sample of your data, then what you would calculate there is what is called the standard error, which would be, you would then grab this definition of the standard deviation of the sample, and then you would divide that by the square root of n. So this is to say these symbols, sigmas, can be saturated. They can mean different things, and so you have to be a little bit careful what you mean in each scenario. Here, what we'll be thinking about is just the standard deviation of the sample of the population, okay? Because we're going to be sampling subsets of the whole data set, okay? We're never going to access the full data set. So in this context, this is going to be the most useful for us. Again, it doesn't quite matter in general. We're going to be just using this formula and try to apply it in different scenarios. Okay, so that's hopefully clarification number one. Clarification number two is that people were asking, what do histograms plot mean, and what do they show us? And so to illustrate this, I figured I would give you an example, and I just did this last night. So it's most useful to think about histograms in a particular example. So let's just generate a random array. And in fact, I would encourage you to do this with me. So let's do it all together. So pull up your terminal or Jupyter or REPL.it. And what are you going to need to do? You're going to need to import NumPy, right? So I'm going to use a terminal because that's my favorite and I know how to work it. Ooh. So by calling Python, IPython, and Pylab, which is what I just did above. Where did I do that? Over here. Automatically NumPy and matplotlib are installed. So that makes my life easier, but I can still do import NumPy as MP if I want to. And so let me generate a random sample of points that are, so I'm going to randomly sample 20 points from 0 to 1, okay? And so this is me doing that, okay? And we already introduced this in the last class, so you're familiar with this functions, random. And so this generates some numbers that are randomly distributed from 0 to 1. And I've done this, I did this last night, and you can see this. It looks similar, right? The numbers are different because they're random, right? And so what we're going to do is make a histogram plot of this data set, and we'll break this up into 5 bins. Why? Because I chose to do it in 5 bins. We can do it in 10 bins, 6 bins, whatever you want, okay? So I'm just going to consider 5 bins, okay? And then the way that the histogram function defines the bins is that it defines them to be evenly separated from the minimum value of X to the maximum value of X. And so imagine, let me go over here. So on the x-axis, what is going to appear, so on the horizontal axis, what's going to appear is the possible values that X can take, okay? And let me call the minimum value X min, okay? And the maximum value X max. And so in this case, I want to divide this up into 5 bins. And so what the histogram plot does is that it grabs this and it divides it up into 5 evenly distributed bins. 1, 2, 3, 4, 5. Okay, and these are supposed to be evenly separated, so I can try to make it a little better. All right, roughly like that, right? And so what it does is that each one of this, the length of these is delta X, where delta X is equal to X max minus X min divided by 5. Okay? And so then the next thing that it does, in this case, let me look at the min value. So the min value of X is equal to 0.068, right? And then the max value is going to be close to 1, so 0.98, okay? So that's the first thing that it does. And what you can see is that when you're going to call the hist function, it prints out the list of numbers that are in the lines. So what it prints out are these lines associated. So it prints out this number right here, this number right here, this number right here. So what it prints out are those 6 numbers. Notice I'm dividing it into 5 bins, and the 5 bins are defined by 6 numbers. And so that's what it prints out. The second thing that it prints out are those 6 numbers that define the 5 bins. The thing that it prints out on the top is a number of instances in which there's a point inside of the bin. Okay, and so we can here. It takes a little bit of time, right, to check this, but then you can see. Let me just plot it. And a plot is generated here. And one thing to note is that some of you have struggled to reproduce some of the things that I do at home because I don't show plt.show, and that is automatically as a consequence of IPython. So IPython doesn't require to call plt.show, which you do have to implement in your own code depending on the platform that you're using. And so you can see that the smallest number here it's 0.07-ish or so, which is pretty close to the minimum value. And then the largest number is 0.98 or so, which is pretty close to the maximum value. You can see that in my interactive plotting scheme, you can see some numbers that appear here, and those correspond to the X value and the Y value of where my cursor is at. That's one of many things that I really like about IPython. And so you can see that things are evenly distributed. You have bin 1, 2, 3, 4, 5, and then the height of it is defined by the number of elements in each. And you can see that what is being printed out is just that 7, 4, 2, 3, 4. So 7, 4, 2, 3, 4. And then if you sum this up, you should get 7 plus 3 is 10, 4 plus 2 plus 4 is 10, so you get 20. So you get all the elements that were available in X. So what is being plotted is the number of instances of the number of events that are happening in between this line, and this line. So how many values of X are on the bottom end? So you have, I'm going to fail at this right now, but that's the idea. Hopefully that makes sense. So it's not absolutely clear what a histogram plot is doing by the end of today's talk or right now, perhaps, why don't you send the message to the question, why don't you send us a question, and we'll try to clarify it even further, okay? But hopefully that clarifies things quite a bit. And I think it's useful to just look at this, play with it yourself, do different examples, right? And so here I did 5 bins, but I could have done 6 bins. And so you'll see that there's a new plot on top of my old plot is being plotted right on top of each other, where the binning is now is different, right? So the bins are smaller because there's more bins in the distribution. So I can do 10, and you see the distribution looks different depending on how I do my binning, okay? All right, so hopefully that clarifies things. And so what I figured I would, so here are some of the useful functions that we introduced last time. You already saw this slide before. And so just try to get familiarized with these functions. And the project that we introduced in the end of last class was to get you to try to calculate pi using random numbers. And there was so I gave you some steps towards doing that, and I saw some people were reproducing some of my code, so that's great. That's exciting to see. I would like to see more of you trying to do this, and I would like to hear, perhaps towards the end of this class or at any point, what are the things that are giving you a little bit of struggle? What are the things that are confusing you? So we can try to clarify it. And so the steps that that we proposed was to generate a random set of X and Y. And here I kind of took a little bit of a random walk, no pun intended, towards getting you to generate points that are inside of a square that is centered between 1, -1 on the x-axis, and then 1 and -1 on the y-axis. And so the whole idea is to just generate random points in between the box, and the points that land inside of the circle, we're going to separate, and we're going to count those separately, okay? But the total number of points in the whole box. That should be an input to your code. And so we'll call that NT, or you can also define it as MB plus MR, where MB are the blue dots and that land inside of the box, inside of the circle, and the red dots are those that land outside, okay? And so the total number of points is just the blue plus the red. And so the point is that the probability of you landing inside of the circle is equal to the number of points divided by the number of blue points divided by the total number of points, which you can calculate. That's the point of this, right? But it's also equal to the area of the circle divided by the area of the square. We know what the area of the square is. It's just 2 squared, since we've set the radius to 1. So it's just 2 squared, which is 4, great. And then on the top, the area of the circle is pi r squared. R is equal to 1, so it's just pi. And that's what you're trying to solve for, okay? So if you solve for pi, you determine the number of loop points divided by the number of total points, and that gives you a way to estimate pi. And so I showed you some code that could make some of these routines faster, but you don't really have to use any of this fancy code. You can just use, and I put my code on the Dropbox folder. Let me show you for those of you that are still trying to navigate the Dropbox folder. So if you go to Python or P4P_2020, you'll see project #3, and this is, so you'll see my slides, which I need to update. You'll see some data that you're gonna have to analyze next, so we're gonna go there next. And then here you'll see my code, which I've called RB code, and then calculate pi, okay? That's the code that I'm talking about. So you can open it up and take a look inside. It's, you know, a little bit long, but you can make it shorter or longer. But I put a lot of comments, and so hopefully that makes it less daunting. So it's longer because I put comments, okay? And so take a look. If there's anything that doesn't make sense, scream out to me, and I'll try to walk you through it if there's any confusion. But as always, I encourage you to just write your own code. Try to solve this using whatever creative tools you can solve and you can acquire. And I'm sure that you might come up with ideas that are better than mine. And so the goal is to get you to plot pi, the value of pi that you're determining, as a function of the number of dots that you've used to fill up this plot. And so you can see that here my number is oscillating a little bit depending on the number of points. It kind of oscillates around the actual value of pi, and then at sufficiently large values of the number of points, I start to converge, which is what you expect. And then I put more extra challenges, and so I'll be interested to hear if people have been able to tackle these challenges, or if there's any confusions, please ask away. And the idea is to try to estimate the error associated with a finite number sample. And so here you can see that I've generated a distribution of points where I've done this over and over again for 100 points, and then I'm getting a distribution of values of pi, and then I see that the distribution is centered around the mean value coincides with pi much better than each individual point. And remember, this takes us back to this example this is very analogous to the example that I mentioned about the ox in the stock fair, right? Where people were asked to guess the weight of the ox, and each individual person got it off, but the average coincided very well with the actual weight of the ox. And so you can see here that if I randomly sample the value of pi using a small set, each one of them gets it off, and the distribution is quite big, but the mean value is remarkably close to the actual value. So it's pretty amazing, okay? And you can see that my errors also decrease with the number of samples that I take, which makes sense, because each one individually gets increasingly more precise with the number of points, okay? And the last thing was trying to get you to make a histogram plot where you show the distribution for a finite number of points, and you can just repeat this experiment multiple times and get pi at different values and make sure that the average coincides, pi with pretty good precision, and that indeed your standard deviation encompasses roughly 68% of the distribution. It's not going to be exact because we're only getting a sample of the full population, but it should be pretty close. Okay, I think that summarizes everything that you've seen so far that we introduced on Tuesday. Maybe I can stop for a second and see if there's any questions that are coming up that we could try to clarify before we jump into a new topic.
Yeah, we had a question from on the live questions feed from Luis Ortiz from Hidalgo, Mexico. They ask, what would be the difference if I is different from 1 and it was 2, 3, etc.? What does it mean? I believe he's referencing the summation index I.
Yeah. Oh, here? Like in the average?
Yeah.
Let's go to the average because that's easier. This right here?
Yes.
So what is the question again? Can you repeat it?
So the question is, what would be the difference if I is different from 1 and it was 2, 3, etc.? What does it mean?
Right. So this summation notation, if you haven't seen it before, it's a symbol. So x bar is equal to the sum of points that start from 1 to n of xi divided by n. Okay, so that's the definition of that. But let's just think about this symbol. If you haven't seen this before, or perhaps you've seen it and forgotten it. So this letter, sigma, is the Greek letter for S. So it's a Greek letter for, so it's Greek capital S letter, okay? And you can remember that this essentially what it's telling us is to sum, okay? Hence the S, hence the sigma, okay? And sometimes you will see that this is not written like this, and you can see that in my slides is written as the symbol where it starts is on the bottom. It's in front of it rather than the bottom. These are equivalent. These are exactly the same thing, okay? They're just different ways of writing the same thing. So don't get confused by that. What does this mean? This means literally to sum all the elements of xi that start with I from 1 all the way to n, where n has to be greater than or equal to 1, okay? And so here we're going to just assume that it's greater than 1. And so what it means is that I just sum x1. Let me actually make n equals to 5, just to make it simple. Let's not make things too abstract. Then what this means is I'm going to sum xi from 1. I'm going to sum the i's. So I'm going to sum xi from I equals 1 all the way to I equals 5. And so it includes 1, which is my starting point. Good. It includes n, which I've set to 5 in this case. N is just a generic placeholder for an integer, just a number, which in this case I chose to be 5. Okay. And so I've included every single point in between. So x1, x2, x3, x4, and x5. Does that maybe clarify the question?
I think it should.
Okay. If not, maybe just send us back a comment. We'll try to clarify it.
Wait, can you hear me? My mic's been kind of awkward all day.
Yeah, we can hear you, Greg.
Awesome. So one thing you might want to add for the lower index when talking about that is that if you had a set of like 5 numbers to be summed in order, if you started at 2, you would just exclude the first number. So if you're
meaning,
so like
you think is that like what if x it starts at 2?
Yeah, that was what I took the question to be.
Very good. Perfect.
Yeah,
we can consider this example too. So imagine that I doesn't start at 1, but it starts at 2. Then what you do is just write x. You start with the lowest number. You replace xi, the I in the xi with the slowest number, which is 2. And then you go all the way to the top. Okay, and so you can do this with any number, right? Let's say I from 3 to 4. Well, this is going to be just equal to x3, which is the smallest one. And then I'm going to sum in steps of 1 all the way to the top one, which is x4. Okay. Maybe that covers the question.
Yeah, I think that hits what I took the question to be at least.
Sounds good. I see some cool Feynman diagrams in your whiteboard.
Yeah, I'm trying my best.
Okay.
Another question that we might want to hit before moving on comes from Decays in Virginia, asking where the points on the histogram were coming from and whether it was just from multiple different trials.
which histogram? Do you have an interest in what they might be referring to?
I believe that when you were going through, the way I took the question to be is when you were going through the multiple examples like live, you had plots on tops of plots. And
oh, this right here.
Yeah, that.
Yeah, so that's just me plotting the same distribution, so the same number of points. So the histograms are a useful way for you to display data, but there's a little bit of freedom as to how you display it, right? And so here, the data that I'm displaying is X, and here it is. X is just these numbers, okay? Now I'm going to try to project this into a figure that I can look at. And a useful one is histograms, right? And so histogram plots, they do what I just mentioned. So here I've divided it into 5. And so it generated, it just grabbed this data and then it separated into 5 different, and then it plotted the number of occurrences inside of each bin. So 7, 4, so forth and so forth, okay? But there's a little bit of freedom, right? If I'm not being told specifically, how do I break up this data? And there's no physical meaning to each one of the bins. It's just an illustration for me to look at. I can maybe use this. I can replace it by, let me not do 3 because it's going to look too terrible, but let me do 7, right? And so you see that what is being shown now, the blue one was when I separate into 5 bins. Now I'm separating the same data into 7 bins, and this is what it looks like. It's the same data. Nothing has changed. It's just how we visualize it that has changed, okay? And I can do this, and so I can do this in 20 bins, and so what I should get is, oh, okay, well, okay. So 20 bins, I can do this in more than the number of bins. Can I do it? Let's do it in 40. Yeah. And so you can do this with any number of bins. It just projects the data. It makes it look a little bit different, but it's the same data. So it's not different trials in this case. Perhaps you, in case you were thinking about this data distribution of my determination of pi, here I am plotting different trials, different determinations of pi, where in each, I've done this many different times, and 45, something like 37 of the times I get this value, 3 of the times I get this value of pi, and so forth and so forth. So in this case, it is different trials. Okay, does that maybe answer the main questions that we have so far? Should we maybe move on?
Yeah, real quick though, Luis Ortiz did come back to us and he says he understood very well about the I index. However, we do have a different question from Abhishek Karki in Virginia. He asks, does the I have to be an integer? Yes, the summation starting point and end point have to be integers.
Yeah. So here, it's just a sum of discrete elements, and the I is just enumerating those elements. The elements themselves don't have to be integers, right? They don't even have to be real. I won't go down that path. They could be whatever. They can be anything. They don't even have to be numbers, actually. They could be strings. All right. Should we maybe move on? Okay, so yeah, Juan?
Well, there was another question related to this, so that's why I think it would be nice to point it out now. It's from Jeju Leo Cho from Shaiji, Taiwan, asking the following. So is the error calculated from the standard deviation, or it is a different from the actual pi value 3.145926? And he asks, how is error related to standard deviation and mean?
Great. So these are great questions. So first, the error. So there's 2 different things. There's a statistical error on the determination, and so this is the point that I kind of skipped over a little bit. But imagine that I've determined pi using some distribution like this, right? I've sampled pi. I asked many of you what pi value is, and then I know that none of you knows pi to, remarkable level of precision, but you all guess it roughly above and below, and I get a distribution. And this is essentially what I've done, just in a smart way, right? And so I make a distribution of pi. Then there's the mean value, which is my guess, my statistical guess for that value, okay? Then there's the standard deviation of that distribution, which is this, which is where 68% of the distribution lies, roughly. So it's telling me how distributed the guesses are. You imagine that depending on how good your mechanism. So here is, you can see that in this case, I'm doing very good at guessing the value of pi, and it gets better and better, while here the distribution is not so great, right? But the mean values, you see that they don't differ that much. And so that might suggest that the error on the mean value is different than the distribution size. And this was what I call the standard error. So the error on the mean value is estimated this way. You grab the standard deviation of the sample, you divide it by the square root of n, okay? This is the statistical error on the mean, but this is not the systematic error on my quote. This doesn't tell me how far away I am from the true answer, right? I could be sampling, I could have started with a mechanism to determine pi that is just completely flawed, and I'm just getting a very precise value that is very far away from the actual value. And so that difference is referred to as a systematic error. That is much harder to estimate in general, okay? So that the statistical error doesn't necessarily tell you how good your result is, but it is telling you how good you're acquiring that value from the statistics, okay? Different issues, and something that takes quite a long time for everybody to digest, myself included. So let's maybe move on. We can maybe come back to these points later on, okay? Does that kind of address the question, Juan?
Yes, I think so, and that's why I brought it in, because I believe that was very important to make this distinction between statistic and systematic. Was a good point to introduce this concept. So yeah, I think that we can.
That's very good, and I hinted at this at the beginning of last class when I started saying that even in theory, when we do a calculation, sometimes we use tools that get us at the answer approximately, and so even then we have to assess errors, and those errors are more commonly known as systematic. But okay, so why don't we move on? Why don't we introduce a new topic where we can start doing some data analysis as well? And so I figured to start with a little bit of overview of some of the forces that we know in nature, and zoom into one particular one of those somewhat quickly. And so, as many of you know, as far as we know, there's 4 fundamental forces in nature. In fact, if you find out about another one, you will most definitely get a Nobel Prize, or somebody associated with whatever experiment you are involved in will get a Nobel Prize, okay? So this is even being able to identify that there's 4 fundamental forces in nature is quite an achievement, but there's many people out there working and trying to extend these. And of course, you're familiar with most of these, I hope. So you're familiar with the gravitational force, which is pulling you down to the Earth, and it's the same force that the sun and the Earth feel, right? You're also hopefully familiar with the electromagnetic force, which is the one that is responsible for allowing us to talk right now, among many different things. And then we have the strong nuclear force, which is basically the bread and butter of our group. So this is the force that attracts protons and neutrons to form light nuclei, but also binds quarks and gluons. And you heard a little bit about this from Ted. And then there's a weak nuclear force, which is responsible for radioactive decay, among other things, and is one of the main mechanisms for the decays of neutrons, and also is remarkably important in the formation of light nuclei in the evolution of stars. And so these these 3 particles can be combined, or not these 3 particles, these 3 forces can be combined into what is known as the standard model particle physics, which essentially describes everything that we see up to gravity, right? And trying to unify these 3 with gravitational force is an outstanding problem that many people are working towards. But just even being able to unify these three, and the last unification, the last missing piece in the unification of these three was in the discovery of the Higgs boson. And I mentioned to you a couple of times that if you're interested in learning about the Higgs and this experiment at CERN, we'll have a talk about this from Max Hansen shortly. And so these three forces are tied up in the standard model. The force that I mentioned is the bread and butter of our group, is the strong nuclear force, which is described by a fundamental theory known as quantum chromodynamics. Chroma referring to color, not actual color, as Ted mentioned. So it's a charge-like quantity that comes in different types. Physicists are a bunch of hippies, and so they decided to make that charge, since it comes in three different types, refer to it as color. It's a little more complicated than that, but basically is a cute way to describe it. And so the modern day nuclear physics is interested in understanding how atomic nuclei are composed, and they're composed of protons and neutrons, but more importantly, how do these come together to form atomic nuclei? And so one example of atomic nuclei are, for example, that of carbon, which is composed of 6 protons and 6 neutrons and is basis of life. So some of the questions that we're interested in is how does carbon itself form, and how do these protons and neutrons come together to arrange themselves inside of carbon? And these, of course, are bound together by the strong nuclear force. But it turns out that protons and neutrons are themselves made out of other quarks, other particles named quarks and gluons. And so nuclear physics, modern day nuclear physics, is interested in understanding all of this, going from quarks and gluons all the way to the upper ends of the periodic table, and trying to unify our understanding in all this. But I'm not going to be talking about this today. I just couldn't help myself. The thing that I wanted to talk about is we're going to do a little example of decays. So that's a little more tied, and in fact, it's also tied to a strong force, and there's decays also in the electromagnetic sector. But it could maybe more commonly be connected to the weak nuclear force. And so what we're going to be thinking about are decays that are similar to the neutron decays. So the neutron itself, even though the formation is one of the particles that are the basis of the formation of life, it actually is unstable when it's on its own. It decays to a proton via the weak force, to a proton, and it emits an electron and a neutrino. Okay, and if you're familiar with charges, you can see you know that the neutron itself is neutral, hence its name, neutral. The proton is charged; it has a positive charge. The electron has a negative charge, and the neutrino is neutral. And so the total charge of the final state is 0. You have +1, -1, +0. That's 0, which coincides with the charge of the initial state. And this is interesting. What we're at the point right now in nuclear physics is that we're for the first time able to determine these types of decays directly from the standard model. And most recently, there was the most precise calculation of this decay was carried out by 2 of our colleagues, Kostas Orginos and Chris Monahan, in Jefferson Lab, and it was published in Nature. So this is even though this is a very well-known, historically well-known decay process, being able to show that it happens directly from the fundamentals equations of the standard model wasn't achieved until recently. And so this is still, being able to understand these decay mechanisms is still an outstanding problem. And so what we're going to do is try to mimic this decay process, and we're going to give you data for you to try to deduce the masses of the particles that are decaying, in particular one of them. And to do that, I need to introduce some basic stuff that I'm going to assume that you haven't seen, in case you haven't, and if you have, you can take a nap. And so these are first momentum, and so momentum is a quantity that quantifies if a particle is moving, and essentially is a quantity that is quantifying how hard it is to stop a particle period, to stop an object. So if the object is moving at no motion, so if it's not moving, then it's super easy to stop it. If it's coming at some velocity, but it's light, it's also easy to stop it. But if it's coming at some velocity and it's heavy, then it's going to be harder to stop it, right? If you can stop, you throw me a baseball, I can stop it. If you throw me, a ship, it's going to be much harder for me to stop it, right? And so momentum is essentially that quantity. It's a quantity that is equal to the mass of the object times the velocity of the object. And the velocity, of course, is a change of position divided by the change of time. And so in Newtonian mechanics, momentum is just equal to mass times velocity. And you're probably familiar with this. One of many things that Einstein taught us is that this is really just an approximation of the momentum that a particle in general carries. And in general, so let me use so in general, the momentum of a particle is still dependent on the mass and dependent on the velocity, but it has this other factor on the bottom, okay? And so this is equal to, so momentum in general, according to Einstein, is equal to mv divided by minus v squared over c, where c is the speed of light. Which is 3 times 10 to 18 meters per second. Okay, so if the speed that the object is traveling, if v is much, much smaller than c, okay? Then 1 minus v squared divided by c squared is approximately equal to 1. And so if the object is moving at very, very slow velocities, then p is approximately equal to m times v. Okay? And so this is the momentum that you're familiar with in Newtonian mechanics, but the one that really appears the one that we know is true in general is this one, okay? And to make matters worse or better, we're going to use a set of units where everything is going to be written in terms of units of the speed of light. And so we're going to set the speed of light equal to 1, just for fun, okay? And in fact, these are units that I live in and most particle physicists live in. And so we're going to be using this expression for momentum, but we're going to be setting the speed of light equal to 1. So then that means that the velocity is dimensionless in this world, okay? This means that time and space have the same units because the speed of light is equal to 1. Okay, and all speeds are dimensionless, right? The other thing that Einstein taught us is that the energy of a particle is tied to its mass, and it's also tied to its momentum. And so if the particle is moving, we know it carries kinetic energy. It carries some sort of energy. And what Einstein found was that E in general is equal to the square root of m squared plus p squared, where p is the momentum, m is the mass of the particle. This is perhaps the less familiar form of the more famous equation that you're familiar with, which is that E equals mc squared, which actually only holds if p, the momentum, is 0, which only holds if the velocity is 0, which means that it only holds when particles are at rest, okay? Also, I've set c equals to 1. So if I grab this equation, I set p equals to 0, I have the square root of m squared, which is equal to m, which equals this equation. So everything checks out, okay? So these are the two background pieces that you need. You need to know the relativistic energy of a particle that is moving, and then you need to know the relativistic momentum, okay? But more importantly, it's the relationship between energy and momentum that we'll be using, okay? And the other thing that we know, and the reason why I introduce energy momentum, is that so far, everywhere that we see in space, energy and momentum are conserved in every single reaction that we've seen in nature. And in fact, when physicists realized that neutrons decay, they could not account for all the energy that was lost by neutrons. And at some point, what was proposed correctly is that some of the energy was being taken away by particles that we didn't see, we weren't able to see, which now we identify as the neutrinos. And the solution was proposed by Wolfgang Pauli. But before that, it was proposed by some, including Niels Bohr, that maybe what we're seeing are violations of energy conservation. But what we know now, at least, is that we haven't seen any violations of energy or momentum conservation. They're conserved everywhere at all instances, as far as we know. Again, if you've managed to find an evidence for this, as I'll say again in a second, you will be a strong contender for a Nobel Prize. So this is just an empirical observation that we found. There's no proof that there has to be that way, but it is the case. And so these neutrinos, which are carrying the missing energy that wasn't detected at the time, are particles that have no charge. They have tiny little masses. At the time, we thought that they were even massless, but now we know that they have masses. And it turns out that they barely interact with matter. So they just fly through us. And in fact, they're flying through us at all instances in time. And they're being created in the sun, they're being created in the inner core of the Earth, and in many radioactive decays. So they're just everywhere. Okay. Okay, so now, let me just, this is my promotion for you to get a Nobel Prize. So now what does this mean? It means that in every decay that we see, and what we have is you have some initial energy of the system. So you have some energy of some system with some energy and some initial momentum. And as you go through the reaction, let me fix this because I just found a typo. The energy and the momentum are transferred to some final energy and momentum. And what we know is that those are fixed. The initial energy is equal to the final energy, and the initial momentum is equal to the final momentum in every single reaction. And so what we're going to do is apply this in an exercise, okay? And this is going to be a data analysis exercise. So hopefully this is clear, simple enough. Now let's start applying what constraints this gives us in a particular decay. And so what we're going to do is mimic a neutron decay. But you see that the neutron decays to 3 particles. And I decided not to be too perverse with you. And instead, what I'll do, instead of a decay, instead of mimicking a neutron decay into 3 particles, what I'm going to assume is that the neutron decays to 2 particles. Okay? And that, so you have an initial particle that then decays to 2 particles. And you're able to see one of them. So imagine this particle has a charge and it's just sitting there. And then it decays to 2 particles. This one has the same charge as the other one. And you can detect particles with charge with minimal problem. And then imagine the other one is neutral, and then it just flies through your detector, and you never, okay? And so the question is, how from detecting this other particle can you deduce the mass of this other particle? Okay, so this is a missing mass problem. And so we want to determine the mass of this particle from this decay process. So, okay, let's do that. So we have a particle with mass 1. That's my initial particle, Ma. And it has, mass of 2. So I'm saying Ma is equal to 2. It's actually a rest. It's just sitting in your, in your chamber. You have it sitting in a little chamber. And then, poof, after some instance, it decays to 2 particles. One of them has a mass of 1. Okay? And you don't know what the mass of the other is. And we will label the other one MC. And what you have to do is find MC. Okay? And so what we have is we're going to assume energy and momentum conservation. And so let me drive this with you. Make sure I haven't made any typos. So what do we know? We know that the initial particle has mass Ma and its initial momentum is equal to 0. Okay? And then at some later time, so his initial time is going this way. And at some later time, here's my particle MC, and here's my particle MB. And what I know, and what I'm going to give you, is the momentum that this one carries. This carries some momentum, MP. Or PB, sorry. And what do I know? I know that the momentum of my initial state, which is PA, is equal to 0. But by definition, this has to be equal to the momentum of PB plus the momentum of PC. So this tells me, since the sum of these two is equal to 0, that tells me that PC is equal to negative PB. Okay, so this means that this guy has negative momentum, negative PB momentum. So that's that constraint, this constraint right here from momentum conservation. Good? The other constraint that I have is energy conservation. Well, I know that my original particle has mass, energy conservation, energy conservation tells me that the initial energy, which is equal to just the mass of the particle, right? E equals mc squared. I've set c to 1, so E equals m. Good. Has to be equal to the final state energy, right? But now I have to use my relativistic expressions for the energies of each individual particle. So it's going to be the energy for particle B plus the energy for particle C. And the particle B, well, it's just going to be the mass of the particle squared plus the momentum of the particle squared, right? So it's this. Plus, now I have to add the energy of particle C, which is just going to be its mass squared plus its momentum squared. But remember, we just found that PC is equal to negative PB, right? And so what I have here really is negative PB all squared, right? But the square of negative 1 is equal to 1. So I just have that. Wonderful. And so notice, the problem is giving you, so you're going to know, we're going to know knowns. These are the things that you're given. You're given mass of A. You're told that this is 2. You're told mass of B, which is 1. Okay? And what I'm going to give you is data for PB. And where does this data going to come from? I'm going to repeat this experiment over and over again, and I'm going to get different numbers. Why? Because the resolution of my experiment detectors aren't perfect. And so I'm going to get, different values that are going to be around the actual value, okay? So I'm going to try to estimate what this value really is, okay? And so then I'm going to give you that, and what you have to do is then solve unknown is equal to the mass of C. That's what you have to determine. Okay, and so I have one equation right here. So I've determined one equation in terms of PB. One equation relating PB to everything else. And so here is how I then solve for MC in terms of everything else. So I just write, let's just do it quickly. So what I do is that I rewrite this equation right here. So I'm going to rewrite this equation. And I'm going to put the MC squared plus PB squared, square rooted. I put this on the Left-hand side, I have MA minus MB plus PB squared. I square both sides. This gets rid of this square root. And then I do, you see, I square this out. And you can see that from both sides, I cancel the PBs squared. And then I'm left with a simpler equation in terms of MC, which is C is equal to minus 2MB squared plus PB. Ta-da. That's it. Did I screw up anything? Sure did. Sure did. Now we're good. Okay, so pretty simple. What you have to do is code this up, right? And so to get you now, the idea is you have to determine what MC is. I'm not going to give it to you. What I'm giving you is the value of PB. And I'm going to give this to you in a list, in a file that is in the Dropbox. So let's go to a Dropbox. So you go to a Dropbox. And let's follow the instructions. Go to Dropbox, then go to P4P 2020 on P3 2020. Then I go to project 3, here it is. And then I see PBS underscore 2B underscore decay dot text. I open this up and look at this. There's a bunch of numbers. And you have 1,000 points. So I'm hoping this is hard enough that you can't go to pulling it one by one and put it into this equation. So instead, what I give you is an example inside of this folder of how to call this data. And you can generate a distribution of the momentum that is being determined. And so if you call this code right here, we can do it together. So let me close that. So I gotta go to Dropbox. Oh, yeah. It's gonna be faster if I do this. Dropbox P4P 2020, project 3. And then I'm gonna do it in IPython because why not? And then I'm gonna import this momentum hist function. And I get this data. I get a distribution of data. And so this is the momentum that is being determined. And your goal is to call this data, and I gave you the key function for calling it is load text. So this just loads the text for you into an array with this file name. And I put the file name here, so you can just copy and paste a lot of this stuff. Okay. And then I made a bin. You see the bin, I made a histogram with bins of 50. You can make this with bins of whatever you want, okay? And then the next step is to grab that data and then determine the distribution of the mass that you obtain and make a little histogram like this. And I want you to determine the mean value and the uncertainty of this. Well, and that's it. It's pretty simple, okay? So it's going to be your first determination of the mass, the distribution. If you want to go fancy, you can determine the error of your mass from the standard error function that I introduced. And so the goal is just to get you to be able to analyze data, put it in through a function, make distributions of another variable and then start analyzing that. So it's that simple, okay? So I think this brings us to the end of today's lecture. This is all that I have prepared for today. We're going to start covering new topics on next Tuesday. Here's a summary of the useful functions that we've played with in Python that are useful for the things that we're getting you to get involved in. And here's some basic equations that we learned today from regarding statistics as well as physics related to special relativity and conservation of energy and momentum. Okay. So what we'll do for the rest of today is try to get you to answer whatever questions and confusions you might have. You can start playing with your code. We can answer your questions in Spanish, whatever you might need. And as always, we're always welcoming your feedback, positive or negative, whatever it is. Hopefully, constructive would be appreciated. And that's all we got for now. So why don't we take some time to answer some questions that you may have, and we can go from there.
We have to wait a bit to come in yet.
Sounds good. Cool. I see from Luis Angel Vergara Ortiz asking if the slides will be available on the Dropbox. Yes, I'll do that right now. So the slides are, some of them are available already, but I'm going to put the latest one. So I just updated this. Also, I would be interested to hear your feedback, and maybe you can do this on the question feature of the live stream, or on the Slack. So you can ask your questions here or on the Slack. I would be interested to hear if you find this pace to be okay, if you have any, if we're going too fast, too slow, if there's any special topics that you would like us to touch on. I have lectures prepared for the next 2 weeks, but we can add something else towards the end. We also wanted to give some opportunity for the researchers in our team to be able to talk about their research topics in the context of Python towards the end, so it would be more advanced, just giving you a little bit of highlights of where this could be useful. There's also thought of maybe giving you guys some projects for you to, if you want to tackle some data analysis. We have interesting data coming along about, cases of COVID. That would be interesting. It'd be also interesting if you guys can do some, at least plotting of the data that is coming, try to maybe do some fits and descriptions of the data with exponential forms and things like that. Would be quite interesting, in particular, since we're all from all over the world. So it'd be interesting to see what the data looks like in different parts of the world where you're in. So that would be an interesting exercise if folks are interested. So we have a question from Indonesia asking if you're, so Brian Go asking if you're allowed to estimate pi using any kind of method such as Ramanujan summation or integral of 1/1 plus x squared. Certainly you can write code for estimating pi in different ways, and you're welcome to do that. The point of this exercise was to play with probability a little bit and also with random numbers. And so you're welcome to try out different estimates of pi. So pi was a secondary, it's not particularly interesting to determine pi at very high level of accuracy, but what's more interesting is getting you the tools to be able to generate these kinds of plots and analyze distributions of data uncertainties, estimate errors. That was the real goal of this exercise, right? Is to get you to have some tools under your belt that might be useful for analyzing data that is more interesting. And so, but you're welcome to play around with whatever you find interesting. I'm not trying to slow you down. Yeah, okay, so we have a question from somebody who didn't put their name or their location. I'd be interested, I'm always happy to see where you guys are coming from. So the mysterious person with no location, if you want to stay anonymous, by all means, but it would be nice if you have a follow-up message saying where you're from, saying, thanks, amazing lecture, thanks. The pace was all right, good. That's what we try to do. Could you please restate the difference between the two different standard deviations? Yes. So the difference is, and I said this point, it's not absolutely necessary for now. I mean, for what we're going to be doing, but the two differences are here. Imagine so one is the uncertainty of the full population, the standard deviation of the full population, and the other one is a sample, is a standard deviation of a sample of the full population. So imagine that I had a full population of, okay? And these represent values, and let me make them. Okay, so these represent values of X, okay? Some distribution. And then I have the full population. So imagine that this was heights in a class, okay? And my class is hundreds of people, like you guys, right? So imagine that I have everybody. Then the standard deviation that I would use, so I would calculate the mean, as I would, right? So I would calculate the mean. So this would be my heights divided by n. And the standard deviation, which tells me essentially the spread of this data, so where 68% of the data lies, is equal to the sum of xi minus x bar squared, the sum of this divided by n, all square rooted. Okay? And this is the standard deviation of the population. Okay? But instead, instead of asking everybody what their height is, copy. Let me imagine that I randomly ask a subset of you. So here is my random assortment. Okay, so I've only asked a sample of you. So this is full population. Okay, and here is a sample. Okay, and the mean, again, is the same definition. But notice here, n is not the same n as before, right? And I'm not sampling the same number of points. So this is not going to be equal to this. This x bar is never going to be equal to this other x bar. Okay? And the definition of the standard deviation when I've done the sampling is equal to xi minus x bar squared and minus 1. And so this is when you would use this equation when you have a subset of the full data so when you have a sample of the full data. Notice also that this is always inflated, right? So this distribution is always going to be, this estimate, well, in principle, will be larger than this one, but it depends on how well you sample the data. So that's a definition. That's the differences of these definitions. When you've done a sample rather than obtain the full distribution. Okay? But again, as I try to emphasize, it doesn't really matter too much at this point. You know, you're just going to apply the formula and just try to propagate it through in your analysis. Okay, so I have a question from Arav Singh asking, what do you do now? Well, it's up to you what you do now. So what I would suggest is, so let me ask you, Arav Singh from the universe, did you do the first problem already? Did you finish the first part of project 3? Did you determine pi? If so, can we see some of your plots? I'm happy to showcase some people's results. Also, if you're done with that, then the next step would be to start doing this analysis. So the goal is start inputting the momentum distribution of this decay. So you have a decay of 1 particle to 2 particles. You have the momentum PB. You determine the mass. You've already given the masses M1 and M2, MA and MB. And then the goal is for you to determine the mass of the missing particle, which is kind of playing the role of a neutrino in this process, because you don't detect neutrinos directly, or you can, but in many decays you don't see them. It seems like the question associated with n versus n-1 was coming from Krish Agarwal from Mumbai, India. So we have a question. I have a question from Pratishan Sarmash saying that they would love to learn about the topic on parts and distribution functions and data analysis related to it. Ted or Fatma, would that be something that we could maybe talk about? Is Ted still on the call? Fatma is in the call? All right. Well, I can say, Pratishan, that I am not an expert on parts and distribution functions, but we have several people that are. So I can definitely look into it. So let me send a message to Ted to see if he or one of his collaborators would be willing to talk about parts and distribution functions in the context of data analysis. I don't think many people, I think most people don't know what that is. I can at least introduce what that is. That's something that I can certainly do, but I would not be able to talk about the data analysis associated with it. So let me send the message to Ted. Okay. Do we see any other questions? I mean, I can continue lecturing if people want. Yeah, so we have a comment from Lucas from Santo André, Brazil, saying, thank you very much for this class. It was awesome. Please, if you could take us through more data analysis project, I would love to take part of it. Great. Yeah, so the next, I can give you a little foreshadow or preview of what we're going to see next. So I'm still developing the material. So the next topics that we're going to be covering Let me see. So things that we're going to talk about are doing fits to data. So we're going to start using some examples of distributions and trying to fit data. So you're going to do an exercise where I'm going to give you data, and then you're going to try to determine the fit for the parameters that I've used to determine this data. And so that's going to require, this is not going to be as simple as what you're doing now, where it's essentially a single parameter fit. I'm going to give you a 2-parameter fit, so it's going to be a little more complicated. And so we're going to introduce things associated with this, and in particular, a function called chi-squared, and then we're going to use this in several different examples. So you're going to be doing a few more exercises associated with data analysis, so don't worry. Yeah. Well, so we can look into the possibility of talking about PDFs, which is what Parton distribution functions are. In fact, I can give you, I don't know what you guys think. Do you think, I mean, it seems like people are moving along and perhaps they don't have questions right now.
Yeah, that seems to be the case. So maybe talk about PDFs.
Sure, I can. In fact, I just gave a talk recently to the program that Alex and Greg are involved in, where I highlighted a little bit about these ideas of PDFs, and I introduced some notions of nuclear and particle physics. And so I can give you guys a little bit of introduction about this, if you wish. Maybe give us some feedback if you want to do this. I'll wait a second. I'll wait 30 seconds. I think the delay is 30 seconds. So if you guys want me to talk about a little bit about nuclear physics, I'd be happy to. And it would take me about 20, 30 minutes. So maybe tell us what you guys think. Well, should I go ahead? What do you guys think? So we have a question from Chesapeake saying, is REYES program going to be available in the future years from now? Well, I think so. The feedback has been really positive. And so I think it is going to be available we're going to try to make it available for as long as possible. And in fact, I might be continuing to do it throughout the year, but not to the full extent of that we're doing it during the summer. But certainly, I think the summer next year, we might be able to do it again. Okay, so I'm hearing some of you are interested in nuclear physics. So when I give you a little bit of an intro to what we do in the group, and give you a little bit of insight into why nuclear physics is important, you're going to hear many of these things from different angles, and so it's useful to hear it from Ted, from me, and some other of my colleagues. And so what I'd like to start with, the idea is, I always like to introduce the theory of quantum chromodynamics, which you've already gotten a little glimpse into it, which what we know is that it's a fundamental theory of the strong nuclear force. And what does fundamental mean? So this is the key point. Fundamental means is that if you ask the question, where is this theory important? In which instances of the universe is important? And the answer to this is that it's important everywhere in the universe and at all instances in time in the universe. That's what it means that it's fundamental. It's that as far as we know, it's been prevailing, it's been present at all instances from the beginning of the Big Bang to now, and it will continue to be present and will continue to play the same role going forward. And how do we understand the first instances of the universe and the role that chromodynamics, this theory of quarks and gluons, played? And what we understand is that in the first instances of the universe was a hot soup of quarks and gluons. And these are the types of reactions that we can mimic the conditions of the early universe by considering heavy ion collisions. So ions are just basically heavy nuclei where we strip out the electrons and then we accelerate into really high energies in which they become these kind of pancake shapes. So they go from spherical to pancake shapes because they're going to really high energies. They smash into each other. And then in that instance, when they're smashed against each other, they're hitting each other at such high energies and such high temperatures that they become a soup of quarks and gluons. And so that the quarks inside of the atomic nuclei get free, and then they start interacting with each other. And this is the same conditions that were at the early universe. Then this soup starts to cool off and expand, and then all the quarks and gluons start to bind together into the bound states of quarks and gluons. And so they start to become a shower of particles. And this is very similar to what happened at the beginning of the universe, where atomic nuclei started to form and come together and then plant the seeds of what would then be stars, and consequently what would then be galaxies. And this theory is not just important there, but it's also essential for the evolution of stars like our very own, where you're seeing right here, you're seeing a video of our own star, where you're seeing a solar flare taking place. In the evolution of the stars, the formation of the stars, the fuel of the stars is driven by the nuclear force, which is described by this one theory. It is also important in the later stages of stars, when stars die and then they collapse. In those instances when the star, sufficiently big stars, the fuel of it runs out, then gravity takes over. So what's keeping stars stable is the gravity that is pushing it in, and then the nuclear energy that is basically pushing it out. Okay, so once the fuel runs out, then the stars can end up collapsing, and then many things can happen. So you can have black holes, or you can have supernovas. So we're going to have a talk on Monday about general relativity, which is a theory that describes black holes, among other things. And so you should tune into that talk by Barsha Terzak, who's a colleague of mine. He's a phenomenal speaker, so I strongly recommend it. But in the cases where you have a supernova, the star collapses, it hits on itself, and then the atomic nuclei can come together and form even heavier nuclei, like uranium and so forth, iron. All these are created in these supernova collisions. But then this theory is also relevant for the kinds of experiments that we carry out at Jefferson Lab, like the GluX experiment, as well as future experiments that are still going to take place, like the electron ion collider that has been recently approved by the Department of Energy by Congress to be carried out by the Department of Energy in Brookhaven National Lab. And so nuclear physics is important now, but it's also going to be important in future experiments. And so quantum chromodynamics, and the line here that I wrote down, which is the same one that I flashed in the next slide, is essentially the one equation, the one needed equation to describe all of quantum chromodynamics, or QCD for short, which in principle should describe all the reactions that I just described. And so our goal as theorists is trying to connect this one equation to all these different rich phenomena that we see throughout in our experiments as well as around the universe. And so quantum chromodynamics is a seemingly simple theory, right? Because you can write down the guiding equation, the guiding mathematical object having defined this, but I don't have to. I can just flash one line and say this describes all of quantum chromodynamics, which describes what you might say. This looks complicated because I don't know what it means, but imagine that just one line should describe all the nuclear phenomena that we see everywhere in the universe. That's profound, right? And that's what it means to be fundamental. And so this one equation encodes the interactions between the existence and the interactions, the properties and the interactions of quarks and gluons. And among the things that the properties that describe them is that they carry color, which is this charged light quantity, And it's called a color because it comes in different types, and they come in red, blue, and green. They're not really red, blue, and green. Physicists just gave them these names, okay? And they also, the quarks can come in 6 different types associated with their masses. And so these were named flavor for fun. And so there's 6 different flavors. And so here are the flavors. They're up, down, strange, charm, bottom, and top, okay? You see flavors, color, up, down, strange. These are quirky, funny things, right? They're funny names. Gluons, also funny, right? But this came from the fact that there was something that was tying the quarks together. So people were saying, oh, maybe it's just a bunch of glue that is tying it together. And sure enough, there are some particles there. And so they were given the name gluons, okay? And so they can be tied in different ways. One of the important rules for how the quarks are tied together is that they have to be in color neutral objects. So they have to be either all in red, blue, and green, or you have to have a red and anti-red tied together. Why anti-red? Well, every particle can have its antiparticle. And for every quantity that we see out there, there has to be an anti-corresponding quantity, right? So the red and anti-red are just, it's, equivalent. So anti-red is just the equivalent of the anti, okay, I'm screwing that up, but you know what I mean, okay? It takes time to digest. And so pions are one example of particles composed of quarks and gluons. They're a particle and an antiparticle tied together. Proton is in a specific way. Protons are particles that are made out of 3 quarks with different, so they have to be red, blue, and green in very specific configurations. But protons are one example, which were made out of states that are composed of quarks and gluons. And so this theory is actually somewhat rich. Even this one line encodes quite a bit of richness. In particular, it describes the interactions between quarks and gluons. And so you can have, in fact, all the interactions that we see can be described in 3 building blocks. One, where a quark comes in and interacts with a gluon, okay? Or, so it emits a gluon, but then it continues to propagate, which is this one. So you have a little line of a quark, it emits a gluon, and it continues propagating. Or you can have 2 gluons fusing into one, could happen. Or 1 gluon decaying into 2, like we were just talking about, like 1 particle decaying into 2. Or you can have 2 particles, 2 gluons interact with each other and then they go off their merry way. Or 1 particle then decays to 3. That can happen. And so there's many open questions in the nuclear world. And one of the challenging bits is that each one of these interactions is proportional to some parameter. And this parameter, this G, it would naturally be a constant, but it's not really a constant. And it depends on the energy of the reaction. So if you're considering high energies, this constant is very small, which leads to the idea that these quarks are almost free, that almost don't interact with each other, because this parameter is telling you how they interact and talk to each other. But at low energies, this constant becomes large. So it's not a constant, it's this function becomes large. And so it makes it hard. This leads to it being challenging to assess, to extract the mathematical or the physical consequences from the mathematical equations that emerge. We don't have a useful tool at this point to reliably extract information from this one equation. And so instead we resort to numerical tools. And so I'll skip this point. And so that's a big part of what our group in Jefferson Lab, and I've showed this picture before, but it's always nice to see. This is what a big part of our group at Jefferson Lab is trying to do, is trying to address these questions of how do we extract physical consequences from this seemingly simple equation. And one of the many tools that we use is a numerical tool known as lattice QCD, which allows us to reliably extract information from the theory without making approximations. And so the focus of our group at Jefferson Lab is threefold. There's 3 broad, big questions that we're interested in addressing directly, in particular in the context of studying the theory of QCD using this numerical tool, lattice, which is we're interested in things that are called nuclear structure, which is how do protons and neutrons come to form the atomic nuclei that we're made out of. So that's number one. And how do they interact, and how do they form the atomic nuclei? The second is hadron structure. So I didn't define hadron. Hadron refers to the generic bound states of quarks and gluons. Any bound state of quarks and gluons is called a hadron, okay? And so the question is, the people that are interested in hadronic structure are interested in is trying to understand how do quarks and gluons come together to form the hadrons. And this is very important because we still don't have a clear picture on this. And this is actually one of the big scientific goals of Jefferson Lab, is trying to understand, and then also the future electron-ion collider is trying to resolve a picture of the inner structure of protons and neutrons, of hadronic states. So protons, as well as neutrons, as well as atomic nuclei, etc. And then there's simpler questions like trying to understand the spectrum of this theory, and this is actually my bread and butter, which is trying to understand what does the state of this theory, just trying to determine the spectrum, look like. And so the question that triggered this whole conversation was regarding Parton distribution functions, which is related to this field of physics. And so let me give you a little bit of introduction on these two, and I think, and I'll touch on what Parton distribution functions are, and I think we can call it a day. So the basic motivation for hadron spectroscopy is basically trying to understand the spectrum of the theory. And this is remarkably challenging. It may sound simple, but it isn't. And in fact, if you've taken a quantum mechanics class, you've been able to determine analytically the spectrum of the hadron, so the excited states of the hadron atom. And if you've done that, great for you, good for you, you pass quantum mechanics, essentially, hopefully. If you were to do the analogous thing for QCD, you would be a strong contender for a Nobel Prize, because it is that challenging. We don't have a good theoretical tool to understand the excited states of, say, even the nucleon. So the first excited state we see in experiment is the so-called Roper, and there's many other different excited states. And these are not, we don't have any theoretical tool right now that gives us a reliable determination of these states, okay? And then the pion has an excited state, which is a pi 1300, and then there's many other different states. And so the field of spectroscopy is trying to understand these states, the excited states of the theory. And the reason why these are challenging is because they're not stable. They don't sit there for you to be able to see them and probe them. In fact, they decay rapidly in instances of 10 to the minus 23 seconds. So much, much, much faster than anything that we would be able to resolve. So they decay to scattering states, just like we talked about decay processes in the weak sector. There's also decay processes in QCD, and so they can decay to 2 particles, like the example that you're playing around with, but they can decay to 3 particles and 4 particles, and it's a mess. It's hard, okay? It's not just hard for people becoming new to the field, but it's also hard for experts in the field, okay? And so this is one of the things that makes this challenging. And right now, this is one of the many theoretical challenges that we're trying to tackle. And the claim is that right now, Lattice QCD is the only tool that we have at our disposal that is promising to be able to study these types of states in an exact fashion. Let me fix this. I'm gonna skip this. Good. All right. And there's various different experiments that are trying to extract the spectrum of QCD around the world. And so I'm just highlighting, so we have, in Jefferson Lab, we have 2, class 12 and GluX, but there's also LHCb there's tons in Europe. There's also BEST3 in China. So various different experiments that are trying to assess the spectrum of QCD. And broadly, they can be categorized into 2 categories: baryons, which are states composed of an odd number of quarks, okay, and mesons, which are composed of an even number of quarks. And so there's the proton, which is a conventional type state, but then there's more complicated states that are composed of 3 quarks and 2 and a quark and antiquark. These are called pentaquarks and have been recently discovered. Then there's exotic states like glue balls, potential glue balls out there that that would be composed of just gluons and no quarks. This is something unique to this theory. There's no good evidence for an actual state of this kind, but there's nothing ruling it out, and so it's surprising that we don't see them yet. There's many candidates, in fact, but it's challenging to isolate them. There's tetraquarks, there's molecules, just like you have you have molecules of different atoms, right? So atomic molecules. You can also have molecules of hadrons that are just much smaller. They're in the, their size would be in the order of 10 to the negative 15 meters rather than 10 to the negative 10 meters, which is what atomic nuclei molecules, right? Atomic molecules exist in that scale. And so what we're trying to do is categorize this, put a picture associated with the different states that we determine. In the world of QC structure, so hadron structure, what is interesting in this case is trying to understand how the quarks inside of protons are arranged. And one of the ways that we probe these states, so not just a proton, in fact, the pion and any hadron, it's really interesting to understand how the quarks and gluons come and merge themselves together. And the way, one way to access this structure is the tool exactly that we use at Jefferson Lab. So in Jefferson Lab, we have electrons that are being accelerated at very high energies and then shot inside of atomic nuclei, in particular, for example, the proton. And then what happens is that if the electron hits the proton with sufficiently high energy, is able to go inside of it and then interact with the quark that is inside. It can also see a gluon inside, and so sometimes these different quarks and gluons and so forth that are inside of the particular state that you're interested in are categorized as partons. Okay, and so this reaction that we see can be described in terms of some function which describes the probability of me picking out a parton, meaning a quark or a gluon, inside of the proton with some particular energy or momentum. Okay, and so these these functions they're non-perturbative, which you can ignore what that means. But these are the parton distribution functions because they're telling us about how the partons are distributed inside of the hadron, inside of the proton. And so ultimately, then in this case, you would have the quark interacting with the photon, which is being emitted by the electron. This would then bounce off. Eventually, you can't have any quarks that are free. This is this notion of confinement, which I kind of gloss over, but quarks can never be free. They always have to be tied together, and they always have to be tied together in a color neutral way. And so here you have blue, red, and the green. The green has to tie to this back up somehow, and it can tie up in many, many, many different ways. And so you will have a shower of different possible final states over here. And so the idea is that you can describe this reaction in terms of the probability of finding a parton inside of the proton, the parton then interacting with the lepton, and then going to a shower of particles. And so this function is telling us about the information of how the parton is distributed inside, how the quarks and the partons are distributed inside of the proton. And so these are parton distribution functions. And so these cross sections can be written in terms of integrals of these PDFs, parton distribution functions, and then more fundamental cross sections, and so or more fundamental amplitudes or probabilities for these partons to interact with these electrons. And so a lot of the experimental work and now even theoretical work is trying to determine what these values of these functions are. How do the partons arrange themselves inside of the proton? And this can give us insight to these basic questions of just how do protons and how do quarks and gluons come together to form the states that we are made out of, as well as many other. So I think that's supposed to be a broad introduction to structure, to QCD structure and QCD spectroscopy, which is a big part of what we're trying to do here at Jefferson Lab. I can see if we can have a talk about how do these Parton distribution functions are analyzed from experiments. We can ask some more experts. I think that could be done. So yeah, we can get back to you about that. But hopefully that was a nice introduction about that. And I think maybe this is a good stopping point because we're 10 minutes away from the time. So let me see if there's any. So we have a question from Brian Go. Let me see if I can understand this. What happens to quarks and gluons after the collision of protons and electrons when it produces gamma rays, photons? Are the masses converted to energy? So I think the question, it's a little hard to decipher the question, but I think it's asking about maybe just to emphasize. So the energy is always conserved, right? So you have some initial state of electron and a proton, and then an electron and some final state. The energy always has to be conserved. The momentum always has to be conserved. That much we know is true for these types of interactions. How does it then get conserved? It can be conserved in many different ways. You can create more hadrons. So your final state can be composed of a proton and a pion, for example. You can create more photons in the final state, which I think is tied to this question, which are real, and those can be created. Those are less likely to be created because the theory of electricity and magnetism is more weakly interacting than the nuclear force, and so those are suppressed a little bit, but those can certainly happen. Maybe that answers the question. But is there anything that you guys are seeing on your end that need to be issues that should be addressed?
Yeah, we had a question from Brian Go earlier as well, and he asks, why do physicists look for elementary particles such as muons, pions, kaons, etc.?
So the question is, okay, so muons are elementary, pions and kaons are not. And what do we mean by elementary? So these are all the elementary particles that we know of. And so elementary particles are particles that are not made out of other particles. And as far as we can see at the resolutions that we can access, they don't have a size. And so they're point particles, which in general can have mass. And that's kind of counterintuitive. And we don't know what the resolution of that is. So we don't know if electrons have a size or not. But they do have a mass, so that much we know. And so elementary particles at this point are particles that have no size, and they're not made out of any other stuff. Kaons and pions are made out of quarks and gluons, and they have a size, which is roughly the same size as a proton. So it's in the order of 10 to the minus 15 meters. So which is large compared to things that don't have a size. Okay, so a proton is much smaller than the hydrogen atom, so it's 100,000 times smaller than the hydrogen atom, but is infinitely larger than an electron, which doesn't have a size. So and same thing for the kaon and the pion. So why do we care about this? Because first, fundamental elementary particles come with rules. They come with if we have a fundamental particle, we need to understand how it interacts with other particles out there. And that leads to equations of this form, where this tells us essentially what are the guiding rules or the fundamental rules of how the universe behaves. And as theorists, that is, or as physicists, is one of our big goals, is trying to understand what are the guiding rules of all the universe. In other words, can we find the equations such that if I, from the beginning of the universe, I put the initial conditions and I press go and I say those are the fundamental equations, can I reproduce all the phenomena that we see? Can we create life out of just these one equations? Can we reproduce, generate sentient life? That's what is meant by fundamental. This should describe all the phenomena that we see in all instances of the universe. And so it's not just the particles, it's also how they interact. We're interested in their dynamics. Okay, maybe that covers a lot of the questions, hopefully. Maybe let me just remind you that we have tons of activities taking place. Also, I think, so you guys, okay, so the Python for Physics people are amazing. You guys are the most active people, I would say, in all Regis, so keep it up, that's awesome. Let me recommend a couple of things. If you want to see videos of things and announcements and previews of what we're doing, if you go to the main Regis page and you click here on the Facebook link, that will take you to Facebook, to the Facebook page for the ODU Regis page. And then if you click the Twitter page, it will take you to the ODU Twitter page. And then here this will take you to YouTube. So follow us in Facebook, Twitter. Also, if you are following, many of you are watching the old Python for Physics videos, the previously recorded ones. That's amazing. That's great. I would also encourage you to look at the other videos that we have out there that have been generated. There's one that I really love, the Kaplan Orchid Conservatory, which is really close to here on campus. It's a beautiful tour of the conservatory. Also, there's many different videos that have been recorded. And I think yesterday we recorded a yoga session. Oh yeah, so the yoga session is already live. And so if this is something that we recorded yesterday, and if you want to relax for a little bit and have, learn about yoga, listen to some interesting music and have a good time, I would encourage you to take a look at this video. So anyways, that's all we have for today. Is there any last minute questions or anything that we have to cover?
No, I think we're good.
Sounds good. So we'll see you next Tuesday. Please do your projects. You have two projects now, number 3 and number 4. Please finish them. Send us your results in Slack. Let us know how we can help you. And do these because we're going to keep building on these kinds of exercises. So we'll see you again Tuesday, and have a good weekend, everybody. All right, you guys good? Cool. We have a call in 5 minutes, no? In a couple minutes. Greg?
Yeah.